and our cosmic journey. We always expect grand structures to evolve at a certain pace, with dense areas like galaxy clusters becoming denser, while space becomes emptier. But do things really unfold as we imagine? Researchers from the University of Michigan discovered that the growth of these large structures is actually slower than predicted by Einstein's general theory of relativity. They highlighted a remarkable phenomenon. While dark energy strongly drives the universe's expansion, the retardation of cosmic structure growth is even more evident than theories predict. Imagine the universe as a vast grid, with galaxies evenly strewn across its surface. Their distribution is not random, they tend to cluster together. In fact, the entire cosmic web started from minuscule matter clumps that gradually grew into individual galaxies and eventually into clusters and filaments. Ben Yin, an astrophysicist and a principal author of this study, along with Phoebe, a student J.W. at the University of Michigan's Physics Department, says that across the universe's history, a small matter clump initially attracts and accumulates more matter from its vicinity through gravitational interactions. As this matter becomes denser, it collapses under its own gravitational pull. The universe isn't just made of matter, it may also contain a mysterious component called dark energy. This element accelerates the entire universe's expansion and has the opposite effect on the formation of large structures. If gravity acts like a magnifying glass, enhancing matter disturbances to develop large-scale structures, dark energy acts like a damper, weakening these disturbances and slowing down structural growth. By examining how cosmic structures have clustered and grown, we can understand the nature of gravity and dark energy. Nguyen, along with physics professor and Dragon Hatter and postgraduate student J.W. at the University of Michigan, tested the time evolution of large-scale structures throughout cosmic history using various cosmic survey tools. Firstly, the team used the cosmic microwave background band photons emitted shortly after the Big Bang. These photons provide a snapshot of the early universe. As they travel to our telescopes, their paths are bent by large-scale structures along the way. By examining these changes, researchers can infer how structures and matter are distributed between us and the universe. To track the recent development of structures, the researchers continued to use the movements of galaxies in the local universe. As galaxies fall into the gravitational wells of cosmic structures, their movements directly monitor structural growth. According to Nguyen, the growth rate disparity we can detect becomes clearer as we approach the present. Separate and combined surveys point to a retardation in growth, or we have some systematic errors in each experiment, or we lack some new physics in our standard model. These findings may address the so-called Sykes tension in cosmology. Sykes describes the growth of structures. The issue arises when astronomers use two different methods, one using then photons, and the other using weak gravitational lensing in galaxy clustering to determine Sykes' value. And they don't match. Both methods do not measure current structure growth, but probe structures at earlier times and then extrapolate those measurements to the present. Assuming the standard model, the researchers' findings of growth retardation at later times could make the two Sykes values fully consistent. Professor Schutter remarked on the high statistical significance of the unusual growth retardation. Frankly, I feel like the universe is trying to tell us something. Now our job is to decipher these findings. We want to further reinforce the statistical evidence for the retardation of the universe's development. We also want to understand the harder question of why structures grow slower than expected in the standard model with dark matter and dark energy. The cause of this effect could be due to new properties of dark energy and dark matter, or some other expansion of general relativity in the standard model that we have not yet considered. These cosmic insights offer a glimpse into the universe's intricate dance of expansion and structure formation, potentially leading us to uncover new physics that will reshape our understanding of the cosmos. The NASA discovery of the farthest black hole, unravel, is a testament to the relentless pursuit of knowledge about our universe. International astronomers, using the Chandra X-ray Observatory and NASA's Hubble Space Telescope, detected signs of a black hole in its earliest growth stages, an event never before witnessed at this point in its life. The mass of the black hole is equivalent to the host galaxy, a striking example of cosmic evolution in action. This black hole was identified within the galaxy zone, located in the same direction as the galaxy cluster Abell 2744, approximately 3.5 billion light-years away from Earth. Furthermore, data from the Hubble Space Telescope suggests that galaxy zone lies even farther away than Abell 2744, at a staggering 2.2 billion light-years from Earth, dating back to a time when the universe was merely 3% of its current age. This discovery paints a grinning future for Earth in a Messier 37 open star cluster, an enigmatic object, roughly 4,500 light-years from Earth, may reveal what lies ahead for our planet in 5 billion years, according to Spacetime. This object is a stunning planetary nebula with a white dwarf at its core, the remnant of a star's recent death. Planetary nebulae, a misnomer from a bygone era, refers to the gas and dust remnants of an exploded star. This fascinating object, discovered by a team led by Professor Klaus from the University of Tübingen in Germany, promises a glimpse into the solar system's future, including Earth, 5 billion years from now. When scientists predict our sun will have exhausted its nuclear fuel, expanding into a red giant that will engulf the nearby planets, including ours. The sun, along with the planets it has consumed, will eventually explode and collapse into a white dwarf, the planetary nebula within Messier 37, with its white dwarf center and a spherical cloud of gas and dust, indirectly represents this future scenario. The death of a star, though long understood, still holds many mysteries. Part of the process remains unclear, especially the relationship between the star's initial mass and its final mass as a dead star. For instance, a star like our sun loses about half of its mass, while stars 8 times larger lose up to 80% of their mass. This might be because heavier stars can consume their nuclear fuel faster by synthesizing hydrogen into heavier elements, thus shortening their lifespan and hastening their evolution into white dwarfs. A white dwarf within the newly discovered planetary nebula has a mass of about 0.85 solar masses, with an estimated living mass of 2.8 times that of the Sun. As a large star, it lost about 70% of its mass upon death. Its surface also exhibits an unusual lack of hydrogen, suggesting it underwent a violent akin to a thermonuclear explosion, which created the planetary nebula. Supernovae provide the surrounding space with the necessary matter for the formation of the next generation of stars. Hence, as we continue to piece together the cosmic narrative, such discoveries serve as crucial milestones, guiding our understanding of the universe's past and our planet's ultimate fate. The relentless march of time and the inexorable forces of cosmic evolution ensure that the universe's story is one of constant change and transformation.